Last time we introduced Peano systems, mostly working with the set of natural numbers, and what we're going to show in this video is that all examples of Peano systems are fundamentally very similar in the sense that they have the same structure. And what we're going to show is that they are isomorphic, which is the mathematical term for having the same structure. Now, just as a quick review from the previous video, what we showed is that the order triple consisting of omega, the set of natural numbers, sigma, the successor function, and 0, which is just a starting element or a zero element, that this order triple is a Peano system in the sense that it satisfies these three properties. First, that 0 wasn't in the range of the successor function, meaning that there's no number that precedes 0. Secondly, that sigma is injective, meaning that when you have this system here, there's no way to get these arrows to somehow loop around to go to a previous number. And thirdly, that the smallest subset, which is closed under sigma, is omega, which means that only the elements you see here are going to be included in the set omega, that there aren't any floating points hanging out. And more abstractly, we showed that the order triple, or we introduced the definition that the order triple n, s, and e is a Peano system if the starting element, e, is not in the range, s is injective, and s is going to be that successor function. And thirdly, the smallest subset, which is closed under s, is n. And the most abstract visualization of the Peano system is going to look like this, where you have a starting element, e, take the successor to get s of e, take another successor to get s of e, and so on. You keep getting these successors when you apply the successor function. Now, what we want to show in this video is that all Peano systems, for example this one, the common one, or even this one, are fundamentally the same in the sense that they look the same. That is, you start with something, take the successor, take the next successor, and so on. And that every such Peano system is going to follow this basic morphology in the sense that they're going to be isomorphic to one another. So we want to show that eventually this Peano system is isomorphic, or it has the same shape as a Peano system that looks like this. And the way we're going to show that is by first introducing recursion. So just to give an introduction to this, let's consider some set A and two functions. Firstly, we have this function h, which is going to take as its inputs the natural numbers, and it's going to output stuff in the set A. And big F, which is going to input stuff from the set A and output to the stuff in A. And let's suppose these two functions h and f are related in this manner, that h of the successor of n is equal to f of h of n. Okay, so you can see that this is going to be what's called a recursive relation, in the sense that I'm not telling you how to compute h explicitly. What I'm saying is that if you have h of like 3, you compute that by doing something like f of h of 2. So suppose we know f everywhere. So if I give you some element in A, f is going to tell you unambiguously how to compute f of whatever input. Well, let's say you only have the value of h of 0, and I tell you that h of 0 is equal to A. And the question I'd like to ask is, can you calculate what h of 3 is from knowledge of h of 0 being equal to A, the knowledge of this relation, and the knowledge of f, what f is doing? And the answer to this is yes, for the following reason, that let's suppose you start with h of 3. We know that by this relation that's equal to f of h of 2, because 3 is a successor of 2, so we just use that relation there. Furthermore, we know that h of 2 is equal to f of h of 1 by that same relation. And working our way downward, we know that h of 1 is equal to f of h of 0. And now finally, we've hit rock bottom. We know what h of 0 is. We know that it's equal to A. So that this expression here is equal to f of A. And since we know what h of 0 is, being equal to f of A, to A, we know that h of 1 is equal to f of A. So that means we can just plug this into this location here, which is make that substitution. So now we know that h of 2 is f of A, and then we just continue to work our way upward. We know that h of 3, since we know that what h of 2 is, we just plug that into this location here. So now we see that h of 3 is f of A. And since we know what f is, we know what a is, and we know what f is doing at each step, we know what h of 3 is. To show the same logic at work, instead of starting from something like h of 3, you could just work from the bottom up, in the sense that we already know what h of 0 is. We know that's equal to a. So we can start to generate the values of things like h of 1, h of 2, h of 3, and so on, just from the bottom up. So we now know that h of 1, just from that relation, is equal to f of h of 0. And we know from the previous line that h of 0 is equal to a. So h of 1 is equal to f of a. So now we've got two values for h. Now we've got h of 0 being equal to a, and h of 1 being equal to f of a. So you can see we're starting to build the table for h. And then we just continue from there. We know that h of 2 is going to be equal to f of a, just because we know what h of 1 is. So h of 2 is f of a. And so on. H of 3 is going to be 3 f's applied to a. And more generally, h of m is going to be m applications of f to a. So you can see here that once I know what h of 0 is, once I know what f is doing, and that f and h are related in that recursive manner, that the function h is determined unambiguously. There's only one such table for h. And the fact that h is determined unambiguously from the starting conditions is given by the recursion theorem. So the theorem is basically saying what we've discovered before, is that let's suppose a is a set, little a is an a, f is some function taking a to a. Then the theorem states that given those assumptions, there's a unique function h taking omega to a such that h of 0 is that starting element a, and that h of the successor of n is equal to f of h of n. And the theorem is saying, just to emphasize, that there's a unique function. It says that there exists such a function and it's unique. There's only one function that it's going to do this. And of course, this seems very intuitive just from the computations that we've been doing before, but of course in math you need a proof for this. And the proof is pretty technical. It's pretty long, but there's really nothing shocking going on. And perhaps I'll make another video just devoted to the proof of the recursion theorem. And now the recursion theorem is going to allow us to prove what we've been interested in. This video is that that Peano systems are isomorphic to one another. So the theorem here is going to say that suppose n, s, and e is a Peano system, then NSE is isomorphic to omega sigma 0 in that there's some bijective function h taking omega to the set n. And now just to introduce the diagram, the set n is going to be all the stuff, all these points down here in the second row, in the bottom row. And then the set omega is just going to be, as it always has, the set of natural numbers. And sigma is going to take elements between that set. And then s is going to take elements between this set. And then h is going to take elements between the set omega to the set n. And the theorem is going to say there's some bijection h taking omega to n, which is going to preserve the successor operations s and sigma and the 0 element. And what that means symbolically is that s of h of n is equal to h of sigma of n, and that h of 0 is equal to e. So that's the statement of the theorem. But let me now try to explain why we care about this equation here. So what we want to eventually say is that this 0 element in this set here is related to the starting element here. And we want to say that 1 is related to the next element after e here, s of e. So we want to have some way of mapping 1 to that element there, 2 to this element here, 3 to that one, and so on. And this is what's going to allow us to say that these two Peano systems here, the one involving omega up here and the one involving n down here, are isomorphic in the sense that I can map each element of one set bijectively to the other one. And to answer the question why we care about this is that let's suppose we start here, that h of 0 is equal to e. So I have 0 here, h is going to map it to e. Now let's say I take s of e. So I'm right here at this point, I take s of e, I move to this point here. So now I've arrived at this point here. So what I want to say is that going from here to here to here should be the same as starting first from here taking sigma, moving to 1, and then using that h function to move from 1 to here. So basically you want to say that the path from here to here to here is the same as the path from here to here to here. And just writing that out symbolically, s of h of n, so we start at n, we apply h first, and then apply s, is the same as starting from n, applying sigma first, and then applying h. So if we have that relation, this symbolic relation here, then this is what we consider two systems to be isomorphic. That they're isomorphic if there's some bijective relation h which satisfies these two properties between the systems. Here's that pair of equations that we're going to be working with. First here, that isomorphic equation, and that h of 0 is equal to e. And here's a smaller version of the diagram I have from the previous slide. So what we have to show is that h is bijective. That's the core of the proof, that h is bijective. So what we already know is that from the recursion theorem, that h mapping omega to n exists and is unique. And we know that this is true from the recursion theorem is if we just take this equation here, s of h of n is equal to h of sigma of n, and we look at sigma of n right here. What does sigma of n mean? Well, that just means n plus. So this right-hand side here is saying the same as h of n plus. And the left-hand side I've just moved over here. So we've transformed this equation into h of n plus is equal to s of h of n. And you notice this is very similar to the recursion theorem, except s is in place of f, but that doesn't matter. So we know that such a function h exists and is unique from the recursion theorem. So what we have to show is that h is bijective. And just to remind you what that means, we have to show that it's both injective, it's one-to-one, and it's surjective, it's onto, or that the range of h is equal to n, is equal to all of n, not just a subset of n. So first I'd like to show that h is injective. So what I'm going to do is I'm going to prove that by induction. So I'm going to set up some set t, where it's all the objects n, such that n is a natural number, and that n being different from some other natural number m implies that h of n is different from h of n. And just like I would normally do by proof by induction, I want to show that first 0 is a member of this set. So I'm going to show 0 is a member of t by contradiction. So let's consider some m that's not equal to 0. So that's the if statement here. Let's suppose that the opposite of this then statement, which is h of 0, is the same as h of m. Now since I assume that m is not equal to 0, it can be written as a successor of something else. So what I'm going to do, I'm going to write m as p plus. So there's some number coming before m since it's not equal to 0. So from this line, I just have h of 0 is equal to h of p plus. And now from the recursion theorem, I know h of p plus is equal to s of h of p. And I also know that h of 0 is equal to e. And notice here we've reached a contradiction because now we've said that s of some input is equal to e, which implies that e is in the range of s. But we know that NSE is a Peano system. That was one of the assumptions of the theorem. And then we must have the statement that e is not in the range of s. So we've reached a contradiction there. And therefore we conclude the opposite, the negation of this statement, that h of 0 is not equal to h of m. And since I've shown that m being different from 0 implies that h of 0 is not equal to h of m, 0 is in the set T. Now let's move on to the next phase of a proof by induction. Let's assume that some natural number k is in the set T. Let's show that that implies that k plus is in T. Now let's consider by contraposition, and what that means is that I'm going to negate this statement here and show that the negation of this statement implies the negation of this statement. So I'm going to eventually show that h of k plus being equal to h of m implies that k plus is equal to m. So let's consider this right here. So again, m can't be 0, and it can't be 0 because you reach a contradiction if you assume that it is 0. So since m is not 0, it can be written as p plus. So I'm going to make that substitution. M is equal to p plus. So I have h of k plus is equal to h of p plus. Now I'm just going to apply the recursion twice. So h of k plus is equal to s of h of k, and h of p plus is equal to s of h of p. Now I know that since NSE is a Peano system, S is injective. So that means that this statement here implies that h of k is equal to h of p. And furthermore, k is in the set T. So that means that if I have the negation of this statement, that implies the negation of this statement. And you can see from that h of k being equal to h of p implies that k is equal to p. Now what I'm going to do is just take the successor on both sides. So if k is equal to p, then they should have the same successor. So k plus is equal to p plus. But remember that p plus was equal to m. So what I've shown is that k plus is equal to m. So I started from h of k plus being equal to h of m implies that k plus is equal to m. So what I've shown there is that k plus is in the set T under the assumption that k is in T. Therefore, the set T is inductive. It's an inductive subset of the natural numbers, and therefore it's equal to the natural numbers. And that gets us to the conclusion that h is injective. Since we know that h is injective, to show that h is bijective, we just have to show now that h is surjective. And that's to say that the range of h is equal to n. And the way we're going to do that is we're going to use our knowledge that NSE is a Peano system, and therefore we know that the smallest subset of n closed under the successor function s is n itself. Now, since we know h is guaranteed by the recursion theorem to be a function from omega to n, we know that the range of h is subset of n. Now, to show that the range of h is equal to n, if we can show that the range of h is closed under the successor function, then that'll get us to the conclusion that the range of h is equal to n. So we want to show that the range of h is closed under S. Just to remind you what that means, we want to show that E is in the range of h, and that for all y's that are in the range of h, the successor of y is also in the range of h. Now this first part, that E is in the range of h, that's already guaranteed, for the reason that we know that h of 0 is equal to E. So we found that input 0, which is going to produce E, so E is indeed in the range of h. So that's true from the recursion theorem. Now let's deal with this second proposition here. Now let's assume that some k is in the range of h, and that's to say that h of some x is going to be equal to k. What we want to show is that the successor of k is also going to be in the range. So we're just going to make the observation that instead of dealing with h of x, let's deal with h of x plus. So let's compute with that. So h of x plus, we know from the recursion theorem, is equal to s of h of x. And since we defined h of x as k, s of h of x is equal to s of k. So what I've just shown is that if x is the input that produces k, then x plus is the input to h, which will produce s of k. So basically I've shown that inference that if k is in the range of h, then the successor of k is also in the range of h. So that means that the range of h is closed under S. And since we know that NSE is a Peano system, the smallest subset of n, which is closed under S, is all of n. So that gets us to the conclusion that the range of h is equal to n. So therefore h is surjective, and we know it's injective already, so h is a bijection. So since we've shown that h is bijective, then that means the picture or the diagram of what's going on has to be something like this, in that h is taking the elements from omega, mapping them to n in this fashion, that this one gets mapped to this, one has to get mapped to that, and because h is a bijection, it can't get mapped to something like that, so it must get mapped to this, then it gets mapped, 2 gets mapped to that, 3 gets mapped to this, And furthermore, the range of h is all of the stuff here because it's surjective. So we know that the picture of what's going on with all those functions, sigma, h, and s, must be something like this picture. So that's why we spent so much time proving that h is bijective. So our conclusion for this video is that all Peano systems are isomorphic to the one that we're familiar with, to the Peano system involving the natural numbers. And the big conclusion is that really all these Peano systems, like this one here, they differ only in the naming of the elements. But in reality, we can say that this element here is kind of like 0, this element here is kind of like 1, this one here is like a 2, that's a 3, and so on. So all these Peano systems only really differ in the naming of the elements. They have the same structure fundamentally. So that concludes this video. Hope you enjoyed this video on Peano systems. And stay tuned for the next video on arithmetic on the natural numbers. And here's a practice problem for this session. And as always, if you enjoyed the video, give it a thumbs up. Feel free to subscribe. And thanks for watching.